So we've just seen that disaccharides are crystalline, sweet, and they readily dissolve in water. Crystalline means they are more like the way we get to see sugar and salt. They are sweet and tasty. They can also dissolve in water. That is because we've got hydroxyls, OH functional groups, and these can interact with water via hydrogen bonds. Now, when it comes to the functions of disaccharides, well, disaccharides, as we can see them being sweet, they can be used to give us energy as for provision of energy. That means we can break down disaccharides into monosaccharides which can produce energy for us. Now, when we are forming disaccharides, disaccharides are formed in a reaction which is called condensation reaction. They are formed in a condensation reaction. Another thing when we're talking about condensation reaction is we can also say dehydration reaction. So when you check on the multiple choice questions, one of these is going to be given. So one of them is going to be an answer. Now, what do we mean by condensation reaction or dehydration? So hydration has to do with water. Dehydration means no water. So a condensation or dehydration reaction is a reaction that releases or produces water. So water is going to be released or water is going to be produced. All right. Now, we are saying disaccharides are temporal storage molecules. Why are we saying they are temporal energy storage molecules? That is because they can easily be broken down. If they were permanent storage energy storage molecules, that means it would be very difficult to break them. But because it is easier to break them, then they are just there for temporal storage of energy. Okay, that is one thing that we need to know. Now, when we are forming, remember we are saying disaccharides are formed from two monosaccharides. So if you have got a monosaccharide A, you mix it with a monosaccharide B, you are going to form a disaccharide AB. And a bond that holds these two monosaccharides is called a glycosidic bond. So whenever you hear of glycosidic bond, it means it's a bond in a carbohydrate coming from glyco, which means sugar. And you know that carbohydrates are sugars. So a bond that is found in a carbohydrate is a glycosidic bond or glycosidic bond. And the process of you mixing A with B to form AB is called a condensation or dehydration reaction. Now, when you break down AB to form A and B, that is going to be called an hydrolysis reaction. So it's just a direct opposite. When you react A and B to form AB, you are going to remove water. Now, when you add water to AB, you are going to break it, and the addition of water to a reaction is called hydrolysis. The breaking of a chemical compound using water is called hydrolysis reaction. Okay, does that make sense? Does it make sense, or we have got somewhere where we are lagging behind? All right. So I take that as a good. Now, monosaccharides, we mentioned three examples. We have got glucose, galactose, and fructose. Even disaccharides, we've got three examples that we're going to talk about: sucrose, lactose, maltose. And we're going to start with sucrose. We need to know its structure, the bonds which are present, and this composition. Okay. Now, what forms sucrose? Well, sucrose is a disaccharide that is made up of one glucose. Remember, we have three monosaccharides, so it's those monosaccharides that are going to come together to form these disaccharides. And so, sucrose is made up of glucose and also fructose. Now, remember, even this glucose and fructose, we talked about alpha glucose and our beta glucose, alpha fructose, beta fructose. When we are talking about sucrose, specifically to specify the kind of glucose which form this kind of sucrose we're talking about, it is the alpha glucose. Now the alpha glucose is going to react with a beta fructose, and because of this, the sucrose that is formed is alpha beta sucrose. Okay. Now because more like fructose is more dominant, we can say, you can think of it in that manner. So the sucrose that is formed here, we call it specifically as beta sucrose. Now we need to understand the bonds which are involved. Well, what is going to happen is this. Remember, you have got glucose and fructose which are reacting. So the carbon number 2 of fructose is going to react with carbon number 1 of glucose. Because of this, the bond that is going to be formed is called alpha 1 comma 2. That is because we have got beta fructose, and the carbon number 2 of beta fructose is reacting with the carbon number 1 of alpha glucose. Therefore the bond that is formed, we are calling it alpha 1 comma 2. Why is it 1 comma 2? Because it's carbon number 1 of glucose with carbon number 2 of fructose. So you always mention the smaller number first before mentioning the bigger number. So this is what we need to know. Now let's just remind ourselves of the structure of alpha glucose and also beta fructose. So we mentioned it that when we are forming these the glucose and the fructose, the ring form, we always use the D form of that kind of molecule you're talking about. So firstly, I'm putting here glucose. At the end, we have got CH2OH. Supposed to have 4 carbons on the middle because we have got one at the beginning and one at the end. One, two, three, four. Now, because we're talking about D glucose, D-glucose, we have got an OH here, we have got an H here, and then we have got OH here, and then OH here. That means we're going to have H there, we're going to have H there, we're going to have OH here, and then we're going to have H here. We said when we're talking about glucose, it should make more like an S, okay, like that, because the OHs are concentrated on the right. That is why we call it D. We say that the second from last carbon, the hydrogen of the second from last carbon is going to combine with the oxygen of carbon number 1. That is going to form an hydroxide, and that hydroxide can either be on top or below the chain, and that is what determines whether it's going to be alpha or beta. Okay, so at this carbon which we've put here, this is carbon number 1. So if the hydrogen is on top, that is going to be called alpha glucose. That means the OH is down, that is the alpha glucose. And that's the one that we are using in this reaction. And we said when we are forming, this compound is going to turn in this direction. That means carbon number 2, the OH is going to be down here. Carbon number 3, the H is going to be down. Carbon number 4, okay, carbon number 4, the OH supposed to be down there. And then we've seen just at carbon number 4 there. Now one thing, let me first put this which has remained. At carbon number 2 we have got an H on top, that's the H there, and then OH carbon number 3 is going to be on top. And then at carbon number 4 supposed to have an hydrogen in there. Now what is going to happen is this. Yes, this is the hydrogen at carbon number 4 that is going to be on top here. So adjust this position. If these two swap, then it is no longer glucose but galactose. Now at carbon number 5, this is the carbon number 5 which you can see here. Carbon number 5, there is a reaction that happens. So this hydrogen that has remained is the one which is going to be down. But this thing which we can see here is the one which is going to be on top, forming carbon number 6. So this is the alpha glucose that reacts in fructose. Okay. Now we are also supposed to have beta fructose. And same, let me first draw a fructose molecule and we see how we get the ring structure. Now at the end we have got CH2OH, and also at the other end we have got CH2OH. At carbon number 2, that's where we've got a functional group. And then, so we have got 3 carbons here, 4, 5, 6. It is more the same just like glucose, but all that differs is that at carbon number 2, that's where we've got a functional group. Okay, like that. And so second from last carbon, which is carbon number 5, is going to react with the carbon containing the functional group. That is what we call the anomeric carbon here. So the hydrogen at carbon number 5 will react with the hydrogen at carbon number 2, forming an hydroxide. Now this is called a Paranos ring because it is a 6-membered ring. It looks like an hexagon. But for fructose, it forms a Furanos ring because it looks like a pentagon. Okay, now let me not put it here because I have to swap something. Let me put it here. Okay, so what is going to happen is this. At this is going to be carbon number 1. At carbon number 1, the OH that has been formed can either be on top or down. But because we are looking for beta, that means the OH is going to be on top. And then this group we can see here is going to be down, CH2OH. And then at this carbon we can see here, this hydrogen that remains here is going to be down, or it can be on top or down there. And then this group which has remained here is going to be down, CH2OH. But mostly the structure to be stable, we are going to have the CH2OH on top, and then the hydrogen is going to be down. And then the rest which remain, if we turn this thing in this direction, we can see that this is carbon number 1, carbon number 2, this is going to be carbon number 3. So at carbon number 3, 1, 2, 3, carbon number 3, the H is going to be down. And then the OH is going to be inside. Carbon number 4, we can see that it's the OH that is going to be where? Down. And then the H is going to be on top. Now remember, for glucose, the carbon number 1 is this one which is here. And we are saying it's carbon number 1 which reacts with carbon number 2 of fructose. And so this thing has to be turned. We need to turn the direction of this thing. So what we are going to see now, let me remove this structure here because we are interested in the ring. Okay. So Casey, just try to check the internet again. Or perhaps it's the same. What are you able to see in the screen?
Yes, I can see.
Okay, Casey, just try to check a bit your network. Alright. And so what we are going to do is we are going to swap this so that where the carbon number 2 is this carbon we are seeing here, I want this carbon number 2 to be near the other one. So I'm going to change the direction. Okay, so what we are going to do is this portion you are able to see this side, we are going to put it this side. We've got the OH there, and then we have got an H down here. Not an H, but a CH2OH there. We've just changed the directions. And then what we are able to see this side, we are going to take it the other side. CH2OH, and then we have got an H here. Okay. And then the other thing, we're also going to swap these. So we're going to have the H here and then the OH here. Yes, Casey.
Is the CH2OH the functional group for?
Okay, the CH2OH is just a group of atoms. So the functional group is the carbonyl. The C double bonded with oxygen. That's the functional group. Carbonyl.
Then what of the CH2OH?
So those are just atoms. Yeah, they are just atoms. We just put them together so that it will be much. It will be a shorter form. Otherwise, if I want to draw that to be CH and then OH, so it will be much longer. It's not a functional. We just atoms together. Is that okay?
Yes.
All right. So now the carbon 2 is now here. So what you are going to see now when these come together, I'm not going to show all the atoms like this. I'm just going to show the important parts. Okay. So now what we are going to see after this happens is these two, this OH which is here is going to come together with this OH here to form a reaction like that. That's how a reaction happens. Now, one of these is going to donate an high OH, the other one is going to only donate an H, and that is going to form an OH. Now, let me ask, which one of these shows for glucose? Where is the functional group? Is it at carbon number 1 or at carbon number 2? Where is the functional group for glucose? Let's see what you are going to answer. Where is the functional group of glucose? Is it at carbon number 1, carbon number 2, carbon number 3, or carbon number what?
I think carbon number one.
Okay. What do others say? Ah, so you people mean you don't know the function, where the functional group of glucose is? Okay. Where is the functional group of fructose? Let me hear. Where is the functional group of fructose? I'm just from mentioning them as I was drawing the structure here. Wow. Fructose, the functional group is at carbon number 2. That's why we are saying the second from last carbon reacts with the carbon that contains the functional group. The functional group of fructose is carbon number 2. That's why we call it a ketone. Functional group of glucose is carbon number 1. That's why we call it as an aldehyde. So what you are going to see is when one of these donates an H, the other one donates an OH, water is going to be released. That is why we call it a condensation reaction. And so what you are going to see is this. We have got an H there. One oxygen is going to remain because the H has gone with the OH. One oxygen has remained, and that oxygen that remains is going to come here like that. And then this bond is going to continue like that. Okay. And then we have got a group that has remained here, which is the CH2 or H like that. So this is how the compound is formed. So this one is gone with one hydrogen here. Only the oxygen that has remained is this oxygen, which we call the oxygen bridge, that connects the glucose and the fructose, forming what? Forming sucrose. Because the bond is formed between carbon number 1 and carbon number 2. And remember, we are using, please know what we are using. We are using alpha glucose and beta fructose. The bond formed is called alpha 1 comma 2 glycosidic bond. That's the bond that is formed. And in some cases, we're going to say that we've also turned this one upside down. Up, just besides us turning it the way it, or the way we had turned it direction like this, we're also going to turn it upside down. We're going to see it like this. So you shouldn't be confused when you see it like this. All we want to form is a bond so that it looks much better. We want to form the bond so that it looks like this. That is why we are going to see we have swapped it. It's all the same. If this OH is on, if the O is on top, the bond is going to look like this. But if the O is down, the bond then is going to look like this. It's really nothing. There's no magic here. Hope we've gotten that. Now look at this. Glucose, the functional group is at carbon number 1. Sucrose, the functional group is at carbon number 1. So both functional groups have reacted. That is why sucrose is a non-reducing sugar. Why is it a non-reducing sugar? Because all the functional groups which are able to reduce, which are able to react, have reacted already. So because of that, there is no free functional group. And so sucrose is a non-reducing sugar. I'll tell you, it is the only disaccharide that is a non-reducing sugar because both functional groups have reacted. So sucrose is the same sugar which we know. In school, you hear someone says, I'm asking for sucrose, meaning they're asking for sugar. So, and sucrose is also a convenient way through which sugars are transported in plants. And that's an exam question. In what form are sugars transported in plants? In the phloem. That is in the form of sucrose. That is because sucrose can easily dissolve. Okay, it can easily dissolve because it has got a lot of hydroxide and such. Is there anything that we've missed? Another thing, another function of sucrose is that it is a sweetener. It is used to sweeten things. Apart from that, it is used in baking and it is also used in the preservation of food. So that's the function of sucrose. It is also used in the transportation of carbohydrates in plants. Do we have questions on that? Any question? All right. I took time to explain sucrose, so the other ones we shouldn't be able to spend a lot of time. So now we are done with sucrose. Let's talk of another disaccharide, lactose. Now, lactose is made from glucose and also galactose. These are the two monosaccharides which makes up lactose. Now, to be specific, it is made from beta galactose. One thing, please, you should know that it is always beta galactose, but it can either be alpha or beta glucose. So if we use beta glucose and beta galactose, then it will be known as beta lactose. If we use alpha glucose and then beta galactose, it will be known as alpha beta lactose. But all we need to know is that mostly we use beta glucose, and even if we use alpha, the name still is going to be called as beta lactose because the most important thing we're talking about is the beta galactose. So for the sucrose, we said it is the alpha sucrose. This is the only disaccharide that is beta. The rest are alpha. It is the only disaccharide which is beta. We need to know that also. All right. Now let's look at the structure for lactose. We already said it is made up from alpha uh, or beta glucose with beta galactose. Okay. Now we need to know which one, what bond is there, what bond is seen in this compound. So let me first draw the galactose. So here I'm not going to show the skeletal formula. We can write it. I'm expecting that we know it now. So the difference between glucose and galactose is just at carbon number 4. So this should be galactose here, and this should be glucose. So if they give you galactose and glucose, you should be able to determine which one is which just looking by looking at carbon number 4 of the compound. So remember the way glucose is. If you really forget, CH2OH, carbon number 2, number 3, number 4, number 5. I don't need that one. Okay. 1, 2, 3, 4, 5, and 6. There's an OH here, there's an H here, there's an OH, there's an OH. So we're talking about carbon number 4. Carbon number 4 is here. You can see the one which you see this side is the one which is going to be below. So whenever you see the OH below, just know that that's glucose. And whenever you see the OH is on top, just know that that's galactose. That's how you tell, that's how you differentiate glucose from galactose. And when you want to determine whether you remember we are using beta galactose, for it to be beta galactose, what should happen? Where should be the OH? Should it be below or on top? Okay. You are sure it should be below? So the OH should be on top, and then the H should be down. That is beta. And then here we are using either beta or alpha glucose, so we don't care. I can use any. So in this case, I'm using also beta glucose. So these are the only points where we are interested. We are only interested at carbon number 4 than carbon number 2. When you want to determine whether it's beta or alpha, and when you want to determine the structure. Okay, Paxina, though I don't know if you'll be able to follow, but our class is starting at very soon, of course. All right. So what is going to happen is this one is going to react with this one. So I'm going to give you a simple research to make. This is an exam question. This is going to come together with this to, but the H, one of these H's is going to come to react with one of the OHs. Now we don't know which one is going to bring its OH with which H. So I'll give you this research. Go and find out which one is going to release the galactose. I mean, between the galactose and the glucose, which one is going to give out the OH and which one is going to give out an H. That's an exam question. Okay, so what I'll tell you is that one of these is going to give an H, one of them is going to give an OH. So when that happens, let me remove this. Remember, there's an oxygen that is going to remain. So the bond that you're going to see, that oxygen that remains is going to be like that. So this is carbon number 1 of galactose and this carbon number 4 of glucose. Therefore, the bond that is formed is called beta 1, 4 glycosidic bond. Beta 1, 4 glycosidic bond. That's the bond that is formed in lactose. Now, lactose is a reducing sugar because the carbon number 1 of glucose is free. And because of this, this carbon number 1 can reduce other substances. That's why lactose is a reducing sugar, because you have got a free functional group, different from sucrose. Lactose Another thing that you need to know about it, it is added in to pills, okay, and it is also added in beer, and it is just used to more like reduce the bitterness in beer. That's why it is added there. Also in pills, it is added to reduce on the bitterness. Now, lastly, just within a short moment, we need to know is maltose. Now, maltose is made from two glucose molecules. Glucose reacts with glucose, and the type of glucose here is the alpha glucose. Both should be alpha, and therefore the bond that is formed is called alpha 1 comma 4. In lactose, we've just said it's beta 1 comma 4, but here it is alpha 1 comma 4, and we know how glucose is already, so shouldn't be a problem for us to be able to determine the structure for maltose. We know that when it comes to glucose, the OH should be below at carbon number 4. So both of these are glucose molecules, so the OH should be below. And they are alpha. So at carbon number 1, where should be the OH? Should it be on top or below? If these are alpha, where should be the OH? Anyone? Where should be the OH? Okay, at carbon number 1, the OH should be below. Whenever OH is below, that's alpha. And so these also are going to come together like this. I'll give you also another assignment. Go and find out which one is going to give out an H and which one is going to give out an OH, because one option is supposed to remain. Please find out just immediately after the class. It is important. So the option that remains is going to be like that. So this bond which is formed here is called alpha 1 comma 4 glycosidic bond. So maltose is normally produced through the digestion of starch. It is then broken down into glucose when you want to have energy. So when you break down maltose, you're going to get two glucose molecules which are going to give you energy. It is important during the production of beer from cereals such as millet, maize, rice. Maltose is very important in that process. Maltose is also a reducing sugar because carbon number 1 of one glucose molecule is free, and it can react to reduce other substances. So this is it on disaccharides.